Good afternoon, class. Welcome to chapter 5. And so far, we have studied, we have a chance to get used to the concept, all the basic concept in warehouse, as well as all the operation principle in the warehouse. And for this chapter, we will have a chance to explore several primary quantitative warehouse planning models. So you can understand how you can transform the all the operation principle into the quantitative model. And this chapter will be divided into three parts. And for the first part, we will have a chance to explore the facility location model, which is widely applied in the warehousing. For example, you can apply this model to solve the warehouse networking, or um, to find the location of several facility within a warehouse in order to minimize cost. Okay, so for this part, we will go through three main sessions. In the first session, we will try to find several ways to classify these models. And in the second uh, session, we will explore the what we call rectilinear distant facility location model. And the last part will be about the Euclidean distant facility location model. Okay, so let's get started. The first part, model classification. Well, a key decision in a warehouse planning is to find the location of one or multiple facility. And there are many ways to classify the facility location problem. So if we based on the number of new facility, we can divide into three main type: single facility location problem and multi-facility location problem, which consist of more than from at least two facility locations. Um, and if we based on the solution space, we can divide this model into two types. The first one is a continuous location problem, in which the location of a new or more new warehouse, more new facility can be located any place within a two or three dimensional region. And the other type, as we call, discrete location problem. So in this type, a new facility must be located only at a specific location. For this facility location model, we also common use two criteria. The first one is minimum location problem, in which we will try to locate one or more new facilities so that the weighted sum of distance among pairs of facility is minimized. And the other criteria is the minimax location problem, in which we will try to locate one or more new facilities so that we can minimize the weighted maximum distance travel from a new facility to an existing or to another new facility. And because the facility location model involved in distance calculation, so we typically use four types of distance measures. The first one we call it rectilinear distance, where the distance are measured along paths are perpendicular to each other, or in Vietnamese what we call it vuông góc. So rectilinear distance is also known as Manhattan distance or taxicab distance because this type of the street layout is really popular in a large city as Manhattan area, which is a major city, a major area in New York State in the United States. So the rectilinear distance between 2 points, if we consider 2 points with the coordinate x, y, and AB, so the rectilinear distance will be equal to the absolute value of x minus a plus the absolute value of y minus b. And for the other type of distance measure as the straight line distance. Straight line distance is also known as the Euclidean distance. So in this measure, distance will be measured along the straight line path between the 2 points. And as you can see, the formula for the straight line distance between the 2 points here. Some of you might recall the Euclidean theorem that you have studied in high school for the perpendicular triangles, right? Okay, so the third type, we call it Chebyshev distance. And for this type of measure, distance between the 2 points in two-dimensional space can be calculated as the greater of the horizontal or vertical distance traveled. So the Chebyshev distance between the 2 points will be equal to the maximum value between the absolute value of x minus a and the absolute value of y minus b. And the last type of measure is the actual distance, in which distances are measured along the actual path between the 2 points. And this actual distance is also known as the flow path distance. And this type of measure is usually used when the travel occurred on a network or along the tree structure. So later in this chapter, you might have some opportunity to actually get used to the flow path distance or actual distance. Okay, so let's move to the second part. Rectilinear distance facility location model. So this type of model will represent a common situation in manufacturing as well as in the distribution setting. because if you have any chance to visit a manufacturing plant or visit a warehouse, you can see that all the street layout within that facility will be um, will be perpendicular or parallel to each other. So that's why we usually utilize the rectilinear distance for the manufacturing and distribution setting. And in terms of the problem categorization, the problem will consider um, several perspectives. The first perspective is the number of new facility. So we will divide them into the single facility and multi facility. And the second aspect is to consider the two criteria, minisum and minimax. It means that for the rectilinear distant facility location problem, we will consider four types. Let's jump to the first type, single facility rectilinear minisum location problem. So this problem will consider to locate a new facility so that it can minimize the total weighted travel distance between the new facility to existing facility. And in order um, to prepare for the quantitative modeling, we will get used to the following notation. So we will use the capital X as the notation for the location of new facility, and capital X will have the coordinate of small x and y. And we use the PI as the location of existing facility I. And for this type of problem, we will assume that we will have the M existing facilities. And the PI will have the coordinate of AI and BI. YI will be denoted for weight associated with travel between new facility and existing facility I. And the distance between new facility and existing facility I will have the notation dxpi. Okay, so the primary assumption for this problem is that the annual cost of travel between the new facility and existing facility I is proportional to the distance between the point X and PI at the constant weight WI. It means that the weight WI will be proportional or will be a representative for the annual cost of travel between the new facility and existing facility I. Okay? So based on the name of this type of problem, we can identify the adjective function for this problem as the total sum of the product Wi multiple d xpi. And because the distance between x and pi's is rectilinear, so it will be calculated as the sum of the absolute value of x minus ai and the absolute value of y minus bi. Okay, so it means that we can rewrite the formulation for the objective function like this. And as you can see that this objective function is actually separable between x and y. So it means that the optimum values of x and y can be obtained independently. So in other words, from one objective function, we can solve these two objective functions separately. Okay, so it means that you can find in the first step you can find the optimum value of x with this objective function, and then in the second step you can find the optimum value of y as this objective function. And because the objective function involved in the absolute value, so it means that fx and fy are actually piecewise linear function. So it means that the optimum value of x and y will be coordinate of existing facility. On the other word, the optimum value of x will be within the value of ai, and the optimum value of y will be within the within the values of bi. And in order to solve this type of problem, we will use the median condition of an optimum solution. So the median condition say that the optimum x coordinate, which we call x star, will be no more than half of the total weight to the left of x star and no more than half the total weight to the right of x star. On the other words, the x star will be between somewhere in the middle of the total weight. Okay, and the common condition for the optimum y coordinate y star is also the same. So in order for you to better understand the median condition, please try to solve this example 1. So in example, we will consider 5 warehouses with the coordinate location from P1 to P5, and we assume that the cost per unit, the unit cost for distance travel between the new warehouse and each existing warehouse is the same. And we have the number of trips per month between the new warehouse and existing warehouse from 1 to 5, 10, 20, 25, 20, and 25 respectively. So for this type of example, you are required to find the optimum location for new warehouse. And in the second part of this example, is require you to find the best location for new warehouse with the location constraint. Okay, so please pause this video and try to solve this type of example for yourself first. Okay, so as we already mentioned in the introduction to the single facility rectilinear mini-sum location problem, so the optimum value of x and y can be obtained independently. So we will try to solve the optimum x coordinate first, okay? So for x coordinate, we have the 5 warehouse with the coordinate AI like this, okay? And with the according weight like this. So the very first step for you is to order the x coordinate of the existing facility from smallest to the largest. So here, the order of warehouse I's will be reordered as 1, 3, 4, 2, and 5, with the coordinate AI increase from 1 to 8. And we also have the weight AI reordered accordingly. So after that, we will try to get the cumulative weight, okay? So for the first one, it will be, so for the first order, which is the warehouse 1, the cumulative weight will be equal to the weight of warehouse 1, which is 10, okay? And for the second order, the cumulative weight will be equal to the weight of warehouse 1 plus the weight of warehouse 3, okay, and etc. So as you can see that the total weight for this problem of all 5 warehouses will be equal to 100. And according to the median condition, we will take the half of 100, which is 50. Okay. So if we apply the median condition for to find the x star, because the x star will be no more than half of the total weight and no more than half of the total weight to the left and no more than half of the total weight to the right. So we will compare the cumulative weight with half of the total weight, which is 50. And as you can see that for the second order, the cumulative weight is less than 50. But for the third order, the cumulative weight will be more than 50. So we will take the optimum value of x coordinate at the third order, which is A4, which is equal to 3. Okay, so why we will take A4 for the x star? Because as you can remember, here we have the optimum value of x will be the coordinate of existing facility. Okay, so x star will take the value among these a1 to a5, okay, and we will take the third order because um, the cumulative weight existing half part of the total weight. Okay, and if we solve for the optimum y coordinate, we also do the same. So the very first thing is to reorder the coordinate bi from smallest to largest, okay? And then take the cumulative order, cumulative weight, and then find which one just exceed the half of total weight. So we will get the y star equal to b5 equal to 4, okay. Okay, so for the second part, in order to find the best feasible solution, we will compute the value of fx. Because here we have three coordinates, right? So we will compute the value of fx for three coordinates. So our objective is to minimize the total weighted distance travel. So among these three calculations, we will choose the smallest value, which makes Q1 as the best site of the new facility, okay? And this is the graph of optimum location for a single facility rectilinear mini-sum location problem. So all the P here represent the location of existing facilities. And X here is actually the coordinate of the new facility. And this dot is the path that connect the existing facility to the new facility, okay. Okay, so the other way besides the medians conditions is to use Excel to solve the single facility rectilinear location problem. Okay, so I already record in order to utilize the Excel tools. I already record all the data from example 1 as warehouse from 1 to 5 with the coordinate AI and the coordinate BI like this, okay. And I also have the coordinate of the new location, and for the new location I will default the 0 value at the first time, okay. And the next thing is to calculate the absolute difference between the x coordinate, which is equal to the absolute value of x minus ai. And in order to compute um, the absolute value, you can utilize the absolute value function in the Excel, which is ABS function in the Excel. Okay, so we will take the ABS function for x minus AI, and then all you have to do is just to copy. Okay, and in order to compute the absolute difference for the y coordinate, you also do the same, in which you will utilize the ABS function in the Excel. Okay, and here are the weight based on the example data, which is really straightforward. And this is our objective function fx. Okay, so the fx is actually equal to the sum product of the weight and the absolute difference for x coordinate plus the sum product of the weight and the absolute difference for the y coordinate. Okay, so this is the first result when we default our x and y as 0. Okay, so in order to use the Excel tool, you need to add the Excel add-in solver first. And if you haven't added the solver add-in, please Google how to add this add-in too. Okay, so all you have to do is just to go to the data toolbar and then choose the solver. Okay, I don't know why it. Okay, so for this type of solver, as you can see that we will set the objective f we will set the objective as here f8, which is the value of our objective function. Okay, and we will try to minimize it by changing the variable cells, which is the variable cells of x and y. Okay, and for this type of problem, we don't have any constraint. It means that there is no constraint to add. So the other thing is to use the GRG nonlinear, because here the solving method, they have the nonlinear, simplex, and evolutionary. So for this type of question, just use the nonlinear method, okay, because it's involved in the piecewise function. So, and then after that you can choose solve. Oopsie. Yeah, you might wait for a little bit for it to run. Okay, so it will return you to this type of this result. Well, let's try to solve this. Well, I'm sorry, I have to close it. Well, it's a little bit annoying that whenever I try to use the solver, I will have to restart it. Okay, so let's try it with the linear method, okay, to see if we can get any better result. So no, no. So it means that it is the best if we choose the nonlinear, okay? Okay, so the optimum value for the fx will be around 440, okay? So that's how you can use the um, solver to solve the single facility rectilinear mini-sum location problem. Okay, so let's move to the other example. So in this example, the coordinate, we have two type of the um, facility of the existing facility. The first type is actually um, represented with a point P1 to P4, and the other type is actually an area. Okay, so for example, for the area A1, as you can see that the x coordinate will range from 0 um, to about 1.5 and etc. So for this type of question, it is impossible for you to use the median condition as the traditional way, right? So there is another way is to use the the graph, which is also the same. So all you have to do for the first step is to reorder the x coordinate from smallest to the largest, and then you will try to graph it like this. So for the horizontal vertical um, horizontal axis, it will represent the x-axis, and for the vertical axis, it will represent the cumulative weight. Okay, so you will have the graph like this for the cumulative weight along the x-axis, and then you will take the half weight line, which is equal to zero point 0.5 because the total weight is equal to 1, and then the cross point between the half weight line and the cumulative line will be the optimum value for x, and you can also do the same to find the optimum y coordinate. So the new unit should be located along the line segment between sig 5 and sig 6 because the optimum y coordinate um, will be any point in the interval y equal to the interval of 5 and 6. Okay, so you can try um, to graph the line for the optimum y coordinate so that you can check if this is true. Okay, so the second type is the multi-facility rectilinear mini-sum location problem. And for this one, we will need to, instead of one capital X, we will need many X, which we denote Xj as the location of new facility J. And we assume that there are n new facility. Pi as the location of existing facility I, which is the same. Wji as the weight associated with travel between new facility J and existing facility I. And Wjk as the weight associated with travel between the new facility J and new facility K. I'm sorry, it should be correct to VJK, okay? Um, the distance between the new facility J and existing facility I as the DXJPI and the DXJXK as the distance between the new facility J and new facility K. So our objective for this type of model is to determine the location of new facilities that minimize the weight of sum of travel between the pairs of new facility and between each new facility and the existing ones. So it means that the objective function can be rewrite like this. And one thing to remind that because the x the because the optimum of x and y can be found separatable independently, so we can divide it uh, into two objective function like this. Okay, so this is the weighted distance travel between pairs of a new facility. Okay, and this part will represent the weighted distance travel between each new facility and the existing ones. Okay, so the first objective function is for x coordinate, and the second objective function is for the y coordinate. And as you can see that uh, on the contrary to the single facility problem. So this multi-facility problem consider the interaction between pairs of a new facility. So it means that obtaining optimal solution is not nearly as straightforward as it was for a single facility problem. What does it mean? It means that we need to find another approach apart from the um, median condition to formulate to solve this multi-facility rectilinear mini-sum location problem. So one approach is to formulate it as the linear programming problem by replacing the objective function, the initial objective function 1 with the following equation. Okay. And here, as you can see that we will start having the constraint. So why can we transform the absolute value of, so as you can see that we transform the formula of absolute value of xj minus xk into the pjk plus qjk with the constraint number 3. Okay, so think it this way. So if, because all the pjk and qjk are non-negative, so if the pjk non-negative and qjk equal to 1, so according to constraint number 3, pjk will be equal to xk minus xi. Okay, so it means that xk minus xi will be non-negative. Okay, and if pjk equal to 0 and qjk is non-negative, then qjk will be equal to xj minus xk, which is also non-negative. Okay, so it means that in that case the absolute value of xk, the absolute value of xj minus xk will be equal to xj minus xk. And we also use the rjk plus sjk to replace the absolute value of xj minus ai. Okay, so the explanation is also the same. So for example, based on constraint number 4, if we consider rji non-negative and sji equal to 0, so rji will be equal to xj minus ai, which is non-negative. So the absolute value of this will be equal to xj minus ai, right? And etc. and so on. So here are the linear programming problem for this type of problem. And when it comes to the linear problem, it is much easier to solve, right? So try yourself to solve this example 3, which asks you to determine the location of the two new machines. Okay, so we will try to solve for the x coordinate first, and then for the y coordinate is also the same. So from the theory above, we can rewrite our objective function as the linear programming formulation like this. And one thing for you to note that because here we have the weight for the weight between the new facility 1 and the existing facility 3, existing machine 3, W313, W14, and W21 and equal to 0. So that's why in this one we will skip them, okay, because it will be nonsense to review all the R and S related to W13, 14, and 21, okay, and we will try to solve this type of problem with the solver Excel. So here we will have the variable as x1, x2, p12, q12, r1, r11, s11, and so on. Okay, and we will set the default value for this one as 0. Okay. Okay, so all you have to do is just to transform the formula here into the formula in Excel. So here I will take the objective function based on the objective function here, right? And I will have the constraint in this order, okay? So the first constraint, for example, will be equal to x1 minus x2 plus p12 minus q12. So it will be equivalent to B2, cell B2 minus cell C2 plus cell D2 minus cell E2, and so on. So you keep doing that, and then all you have to do is just to use the solver. Well, I hate that. I don't know what's wrong with it. So we will set the objective function as b at this cell, right? Okay, and by changing variable cells from B from B2 to O2, okay? Well, I don't know. From B 2, 2, 0, 2. Okay, so this should be B3. Okay, so you will add the constraint according to this. So constraint 1 will be equal to 0, constraint 2 equal to 0, constraint 3 equal to 15, constraint 4 equal to 15, 5 equal to 25, and 6 equal to 40. And the other thing is that because all the unconstrained variable non-negative, so I will check this one, okay? And I will try to solve this with the simplex LP. It means that linear programming. Okay, so and then just click solve, and it will return to you the optimum x coordinate at x1 equal to 15 and x2 equal to 15 with the value of fx at 410. Okay. Okay, so this is the linear programming formulation for y coordinate, and you can also doing the same. So it's just simple that you just copy from this above cells into this with the minor change, minor appropriate change. Okay, so you can solve with the solver cell to get the optimum y coordinate, which will yield the y1 star equal to 10 and y2 star equal to 15 with the optimum value of fx fy at 390. Okay, so by transforming into the linear problem, we can solve the optimum location of the two new facility at x1 star at 1510 and x2 star at 2515 with the total distance travel equal to fx plus fy equal to 800. So the question is, why can we use solver with the original problem? Well, let's try it. Well, I don't know why this has this type of problem. So let me reopen it. Okay, so here, in order to try it with the solver in traditional way, we will have four machines and the coordinate of the four machines, and then we will consider the absolute difference um, uh, of new machine 1 to our existing machine and new machine 2 to all the existing machine, and then the weight for new machine 1 and the weight for new machine 2. Okay, and we also consider the absolute difference between the two new machines with the weight between the two new machines at 12. Okay, and then we will have the decision variable x1 y1 as the coordinate of new machine 1, x2 y2 as the coordinate of new machine 2, And then we will set the objective function based on the original objective function like this, okay. Okay, so we will try to run the solver and see what are we gonna get. Okay, so we will take the objective at these cells by changing the variation cells x1, x2, y1, y2. There is no constraint and we don't have the non-negative constraint, right? And then we will try to solve it. Okay. Okay, so as you can see that well, let me use the uh, simple linear programming. Well, it doesn't change anything. So as you can see that solving this will change nothing. It will give you the non-optimum value, right? Which is far worse than we have with the linear programming problem 800. Okay, and one way to explain that, because the solver produces a solution using a search routine, so it is possible for the search to terminate prematurely and yield a non-optimum solution. So that's why we do not use solver with the original problem, but instead we transform it into a linear programming problem. Okay. Okay. And this is um, what we call to use a coordinate descent, or to use the median condition to procedure uh, to use the median condition procedure to solve the problem in example 3, which is a heuristic method. Okay, so this is the flow chart, how you can use the coordinate descent or median condition procedure to solve the problem in example 3. And please read it carefully, and I will put it in your homework so that you can try to solve it at home. Okay, so far we have done with two types related to the mini-sum location problem, and for the next type will involve in the minimax location problem. So we will consider the single facility rectilinear minimax location problem first. And we will use the same notation as before. So the minimax location problem for a single new facility can be written like this. So we will try to minimize the function, the objective function fx equal to the max of the sum of the absolute value x minus ai, um, absolute value of y minus bi, and gi. So for the minimax location problem, we introduce a new parameter gi, which is the fixed travel associated with existing facility I. Okay. Um, so one way to understand the GI in reality is to look back an earlier example involving the location of emergency response unit. So in that case, GI might be the time required to travel from existing location to the nearest emergency room. Okay, so GI here is actually the fixed travel or the time, which is the time or the cost to travel between the existing facility location and the new facility. Okay, so in order to obtain the minimax solution, we will let C1 as the minimum value of AI plus BI minus GI, C2 as the maximum value, C3 as the minimum value of minus AI plus BI minus GI, C4 as the maximum value, and C5 will be the maximum value of C2 minus C1 and C4 minus C3. And there is one paper who proved that the optimum solution to the minimax location problem are the as the all the point on the line segment connecting between these 2 points. Okay, and I also put this paper into the reference list by the end of this part. So if you want to understand better how this can be the optimum solution for this minimax location problem, please refer to this paper, okay? With the maximum distance equal to C5 over 2. Okay, let's spend some time for example 5 so that you can understand how you can solve the minimax problem for a single facility. Please pause this video to try yourself. Okay, so this is quite straightforward. So based on the data from the problem, you can calculate the AI plus BI and the sum of minus AI and BI for each workstation. And from this, you can take the value of C1, C2, C3, C4, and C5 like this, right? So the problem, the optimum solution are all the points on the line with coordinate x star, y star, and x2 star, y2 star with the maximum distance as 187.5. So this is the illustration of the optimum solution in example 5. So all the dots here represent the location of existing facility, and this line segment as the optimum minimax location. So you can choose any point along this line segment as the optimum minimax location. Okay. Okay. So the lot type for this part will be multi-facility rectilinear minimax location problem. So for this multi-facility um, problem is actually an extension of the minimax location problem um, for single facility, and we can have the objective function like this. So um, like the multi-facility mini-sum location problem, we also introduce the interaction between pairs of new facility. So that's why apart from the interaction between the new facility and existing facility, we also have the part represent the interaction among pairs of new facility at this one. So GJI and HJK are actually the fixed cost associated with the new and existing facility pairs and pairs of new facility. Okay, and this problem can be converted to a linear programming problem. But instead, we can use the solver to solve a small example. Okay, so let's spend some time to solve example 6, which is based on example 1. So we have 5 warehouses with the coordinate location from P1 to P5, and suppose that we consider build 2 new warehouses with the goods flow divided between the 2 new warehouses, and we have the flow data like this with the WJI and the VJK. Okay, so please pause this video and try to solve it yourself with the solver. Okay, so for example 6, all you have to do is just the same. You can record all the data given in the example and calculate the absolute difference between the one new facility and existing facility with the weight here, as well as compute the absolute difference between the 2 new facility with the weight between the 2 new facility at 10. Okay, and then you will um, have the set the value for the decision variable as 0 as default, and type the objective function, which is the maximum function. Okay. Okay, so we will try to use solver. Well, I think that stopped running. Well, let me force squeezing again. I'm sorry for this inconvenience. and try to reopen it. Well, the utilization of this one is just the same. Okay. Okay, so we will set the objective function here, this cells, as the value of fx. And by changing the variable cells like this, there is no constraint, and there is no constraint on non-negativity, so we will not click on this one. And then we will try to use the nonlinear to solve it. Well, so it will return the result with the objective function value at 100 and the decision variable like this. Okay. So, well, some of you might raise the question is, why do we use solver for multi-facility but not with the single facility version of this function, right? Well, there are two reasons. The first reason is that we want to expose you to a variety of ways to solve location problem. It means that we want to introduce to you as many ways to solve this type of problem as possible. The other reason is that solver does not guarantee to produce optimum solution because it's based on the search procedure, and this search can terminate prematurely, which will make the solution likely good but not optimum. So for the single facility version, because we have a way to transform it into um, into other way to solve it. So that's why we will use Delay that way because it will ensure you the definitely optimum values. But for solver, it will not. Okay. Okay, so I think that's all for our lecture today. And for this lecture, if because it's contain a lot of information as well as it's contain a lot of um, models which might give you a lot of confusion. So I encourage you to um, try to solve all the example by yourself even when you have done it before. So just try to solve it, and I will give you the homework for you to practice at home so that you can have a good preparation um, for your midterm. Okay. Okay. Thank you again for listening me. And I hope that you learn a lot from this session.